Good day, I'm Dr. T and welcome to my dining room table. So today I would like to talk about intermolecular forces. These are forces or attractions holding molecules to each other. They're typically going to be much weaker than the forces that are holding the molecules together themselves. So what I'm talking about is not going to be as strong as covalent bonds, usually by a long shot. So in order to figure out what's going on, these are actually going to be a charge difference, kind of an electrostatic approach. And I'm going to give you a few examples to kind of show what's going on with these guys. So let's look at the weakest of the intermolecular forces. So I'm going to start out with the molecule methane, CH4. And you can think, hey, this is a gas. Yeah, this is why it's a gas. Water, which I will cover here in a little bit, has much stronger intermolecular force and is able to hold itself together as a liquid. Small molecules, it's not that hard for them to become a gas. It's easy for them to move fast enough. So if they don't have really strong intermolecular forces, then they're going to be a gas. If they have strong intermolecular forces, well, that's a different story. Okay, so I've got this guy, but I'm actually going to draw the Lewis structure for him, which we did so in another video. And the key thing on this one is to realize that I've got a bunch of electrons in here. So I could imagine this thing being just kind of a ball of electrons. Because in reality, most of this guy is electrons. And it's entirely possible for a fraction of a second, a tiny, infinitesimally small part of time, that there would be a few more electrons just kind of on one side of the atom than there would be for the other side. So that would cause one side of the atom, and you'll see why I'm doing this dotted here for a second, that would cause one side of the atom to be positively charged and the other side of the atom to be negatively charged. Now, the symbol I'm drawing, which is going to become more important when we talk about it a little bit later, this is a lowercase Greek delta. And so delta plus or delta minus indicates a partial positive or a partial negative charge. Now, usually when they're drawn, they're actually drawn to indicate, a permanent one. But right now we have a very ephemeral, there's a little bit less electrons. The electrons are not quite spending as much time on one side as the other. Now, if I redraw this, I'm going to draw this a little bit simpler. So if I draw this CH4, and I draw it kind of as a ball, and I draw another CH4, and I draw it as a ball. And if the electrons are hanging out more so on one side than the other, then I'll have my partial positive and my partial negative, and those will be attracted to each other. And this will cause them to stick together. Now, if you cool methane down enough, the heat's not enough to break this, and they will hold together as a liquid or as a solid. But it's not a very strong force. The bigger the molecule I have, the bigger this force can become. So if I get a much longer molecule, something that is, a carbon, 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 1, 2, 3, 4, 5, 6, 7, 8, and then hydrogen, 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 hydrogen. This is octane, by the way. One of a group of molecules that is in gasoline. Now, this guy has lots of electrons that could be in different spots, creating different regions of positive and negative. And so this guy can kind of scrooch up next to each other. They're differences in charges. They're just ephemeral, very, very temporary. They're simply because the electrons decided to just dumb luck be on one side or the other. And in this case, you have a liquid. It's a large molecule, stronger intermolecular forces. If I was to add many more carbons to this, that would be asphalt. Asphalt is notoriously sticky. Okay, so let's go for another molecule. In this case, we've already done this one as well, formaldehyde Ch2o. Now, in this case, the Lewis structure looks a little bit like this. Now, with this one, it can do this style. This is called London dispersion forces. And this guy, it's got two things going on. So right now, there's no particular interaction between the carbon and the hydrogen. They pull on electrons relatively equally. We say that they have a very similar electronegativity. But oxygen is a much more electronegative atom. So it's able to attract the electrons more so to it. Oh, almost forgot my lone pairs. And because of that, because the electrons are going to start crowding around the oxygen, that's going to give it a partial negative charge. And this is a true partial negative charge. This is not ephemeral. It is a permanent, what we call dipole. We call it dipole because the other end is a positive charge. Now, it's not a full electron. These are not cation, anion kind of thing. There are molecules like that. We call those zwitterion. But this is not that. This is simply an uneven distribution of the electrons. To kind of paraphrase George Orwell, some atoms share more equally than others. But yeah, so this means that I have a charge, and we actually draw these as a vector with an arrow pointing towards the direction of the negative charge from the positive charge. And this is what we call polar. This is a polar covalent bond, and this makes this molecule polar. Now, it gets a little bit more interesting when you've got a couple more bonds doing some interesting things. So let me introduce a molecule that you are all familiar with, good old water. So we have ourselves an oxygen and a pair of hydrogens. Now, two things are going on. One, the hydrogen's very small. So this is going to have a partial negative over here, a partial positive there, a partial positive there. The electronegativity difference is enough that this isn't just a partial negative. It's like really negative. It's not a full atom. It's not an anion. But there's a much more dramatic charge discrepancy here. So in this case, the arrow is much bigger. And there's two of them. When you get this much larger arrow, and you get this when you have oxygen-hydrogen bonds, nitrogen-hydrogen bonds, or fluorine-hydrogen bonds, although that's only one compound. That's HF. Then you get what we call a hydrogen bond. And this one will be an intermolecular force that is about 1% or so as strong as a covalent bond, which is actually really strong for these guys. These guys are much weaker than covalent bonds, where this guy is on the spectrum kind of thing. It's on... This guy is you know, it's within shooting range of the covalent bond. It's nowhere near it, but it's still getting there. And it will actually behave a little bit like a bond. It's not, but it's getting there. Now, with these arrows, since I have a molecule that I have drawn, it has one going this way and one going that way. Well, vectors can be added together. So, overall, water has a polar vector that adds together. So it's got its multiple polar covalent bonds. They add together and creates this polar molecule with this really strong polarity. Water is very polar. It has very strong attractions to other water molecules. They'll line up nose to tail. So in a solution, you'll have water molecules, and they will line up. And you actually see this in ice. When you look at an ice crystal, this is what's going on. And the water molecules will line up nose to tail because the oxygens are negatively charged just slightly. It's not a full electron. It's a partial negative charge. But the hydrogens are positive. Once again, partial, but you know, notable. They line up nose to tail and they all stick to each other nicely. Now, shape matters in this case. So when I have a molecule, I can have ones that I would think would be polar, but they're not. And a classic case is our friend carbon dioxide. So if I draw carbon dioxide, and I draw the Lewis structure of this one, it looks like this. And one of those interesting quirks to it is that it is a linear molecule. Molecules have, you know, shape to them. Normally they start out life as a tetrahedron. So water is a tetrahedron. Now, two of the sides of the tetrahedrons are going to be lone pairs, and two of them are going to be hydrogens. The carbon, this guy, once you have a double bond, that generally takes one dimension out of it. So this is going to look like a triangle. 1 over here and 3 over there. So I have 3 things that turns into a triangle. Lone pairs count as a thing. Well, carbon dioxide, I only have 2 things. 2 things make a line. They're trying to get as far away from each other as possible. We call this Vesper, or valence shell electron pair repulsion theory. Talk about a tongue twister. The idea basically, though, is that each thing, whether it be an atom or a lone pair, is trying to get as far away from the other things as possible, and thus it'll pick a shape that corresponds to it. So 2 things around a central atom, that's going to be linear. 3 things, that's a triangle. 4 things, that's a tetrahedron, which is kind of the kettle-trop shape of a D4 if you're familiar with dice. Now, with this guy, what you're going to have is 1 vector going this way, 1 vector going that way, and it's a tug of war, and it's a tug of war that cancels themselves out. So, always forget the lone pairs. Don't forget the lone pairs. So, the sum of those 2 vectors is 0. While there are polar covalent bonds in carbon dioxide, it's a nonpolar molecule. Methane is nonpolar because there's no polarity in it at all. And when you have a nonpolar molecule, you can only have London dispersion forces. These guys will still have London dispersion forces, but we usually don't talk about them as much because they typically are not that big of a deal. They're not that impactful because they're being overwhelmed by the more powerful dipole-dipole interactions or the extreme dipole-dipole interactions that are known as hydrogen bonding. This is going to have a major impact on things like boiling points, and it turns out things like hydrogen bonding does affect how atoms interact with each other. So things like, the hexane types of oils, those don't interact well with water because they don't share the hydrogen bonding with the water. And the hydrogen bonding leads to this very ordered structure where these are a very disordered structure, and the 2 don't get along too well. So with that said, have a wonderful day, and I will see you in later videos.